Okay, this is the second hour of Physics 1B for October 13th. And we're going to do one more problem, and then we're going to talk about the relationship between temperature and energy, specifically kinetic energy. Okay, so this is a derivation problem. It's not really much of a problem. It's mostly just a derivation. So what we want to do is we want to find the variation of atmospheric pressure with elevation in the Earth's atmosphere, where we're going to assume that at all elevations the temperature is 0 and the acceleration due to gravity is 9.8. That is approximately true, at least over the height of our atmosphere. The atmosphere goes up to about like 30 kilometers above the surface, and the radius of the Earth is 6,400 kilometers, so the variation of gravity is very small over this range. So we want to figure out, how does pressure vary with elevation? And to do this, we're going to use these two equations right here. This is basically the ideal gas law rewritten in terms of density that we derived earlier. And this equation, if you don't remember it, is basically the way in which pressure varies with elevation. And I can write it in another way that might make it look a little more familiar. If I write it like this, and then change delta P here, this is just the variation of pressure with depth equation, basically. That's all that it is. Okay, so we want to use those two equations and come up with an expression for the pressure as a function of elevation, or the height y above the surface. That's what we want. We want to come up with a function, mathematical relationship, that involves all these things here, and y. Does that make sense? All right, here we go. We're going to start with this equation. It says, if I take the derivative of the pressure, I'm going to use capital P for pressure, with respect to y, that this should be equal to negative rho times g. But rho is equal to this. So instead of writing rho right here, I'm going to write pressure times molar mass divided by the gas constant times temperature. And there is a negative sign right here. The next thing that I'm going to do is I'm going to separate the y's and the p's. I'm going to get all the p's on one side of the equation, and I'm going to push all the other stuff to the other side of the equation. This is a special type of equation right here. Does anyone know what it's called? Did I leave off G? Oh, I did, thank you. Sorry about that. What is this equation called? What kind of equation is this? Where I have the derivative of a function, and then the function itself shows up in there as well. Maybe you taken enough math. I think usually toward the end of Calc 2 you talk about this. It's a differential equation, that's right. So we call this a differential equation. And hopefully that doesn't scare you too much. All that means is that it's an equation that has a derivative in it. We've got the derivative, and then we've got the function. In particular, this is the easiest type of differential equation to solve. We call this a separable differential equation. And you will see it many, many times in your study of physics. Definitely in 1C, you may have seen it in 1A when you're talking about the velocity of an object as it's falling and reaching a terminal velocity. Shows up in 1C, it shows up in 1D. Very common that these type of equations show up in nature, and here it is showing up in Physics 1B with pressure and height. So how do you solve them? You basically do what I said. You're going to take all the pressures and get them on the same side of the equation. So I'm going to take dP over P, and then I'm going to move the dy to the right-hand side. So we're going to have negative RG, that's not R, negative mg over RT dy. And then what you do is you integrate both sides. Okay? And we're going to integrate from the ground, where y is equal to 0, up to some arbitrary height that I call y prime. On the left-hand side, we're going to integrate from the pressure at ground level, which I'm going to call P naught, up to some arbitrary pressure that I'm going to call P prime. What do we get on the left-hand side here if I integrate this? Just to give you a picture of what we're doing, we're saying that we're looking at some point here where the height is y prime, and we're saying the pressure down here is P naught, and the pressure up here is P prime. So this is y equal to 0, and this is y equal to y prime. What do I get if I integrate dp over p, or put it in a way that's probably easier for you to understand, dx over x? What does that give me? 1 over p squared. That is not quite correct, is it? Not quite correct. Natural log p. That's correct. So here we're going to get the natural log. Now let's stay in red. Here we're going to get... Please? What do I need to do to click you? Nothing? Who knows? All right, so here we get natural log. For the person that said 1 over p squared, just to help you understand why that's the case, the rule, when I have p to the n, and I'm integrating that with respect to dp, the rule says that you add 1 to the power, and then you divide by the new power, right? So in this case, if I have p to the negative 1 dp, which is what we have, and I add 1 to the power, something bad happens, right? If I add 1 to the power here, I just get p to the 0, which is 1. You know what I mean? If I do p to the negative 1 plus 1, this is equal to p to the 0, which is equal to 1. And the antiderivative of 1 over p is not 1. Right? Because what's the derivative of 1? What's the derivative of 1? What's the derivative of a constant? What? No. 0. That's right. 0. So that's how you know this doesn't work. So this does not work. This works for n not equal to 1. You could have n be 1.5, n could be pi, n could be negative 50, and this will work, but it does not work when n is equal to 1. So that's just to help remind you why it is that it's natural log. Okay. So we get natural log of p evaluated from p naught up to p prime. On the right-hand side, what am I going to get here? Well, I've got mass, gravity, r, and temperature. We've already said we're going to assume the temperature is constant, so we know we can pull that out of the integral. R itself is a constant, we can pull that out of the integral. And capital M is going to be the molar mass of air, also a constant, which we can pull out. The one thing in here that might depend on elevation would be G. Okay. G. But we've already said we're also going to assume that that's constant. So if we pull everything out of the equation, the right-hand side basically becomes negative mg over r times t integral dy. And if you just do the integral of dy, you're just going to get y, right? So the right-hand side is going to become negative mg y prime divided by rt. I'm just going to go ahead and plug in the limits because the other limit's 0. So this would be this minus 0. Okay, but we're not going to include the 0, okay? That's what you get, just that right there. On the left-hand side, we'll have natural log of p prime minus natural log of p0 equal to all this. And then we can turn this into a ratio by using the property of logarithms that if you have a difference of logarithms, it's the same thing as doing this. The next thing that I'm going to do is just acknowledge that when I put these primes on here, p prime and y prime, they're really kind of just arbitrary values. And the only reason I did it was because I wanted to make it so that the variable of integration p wasn't the same thing as the limit of the integration up here. And same thing over here, I didn't want the limit of the integration to be the same as the variable of integration. So at this point, I'm just going to drop the primes. because they're basically just dummy indexes. So p prime is just going to become p, and y prime is going to just become y now, okay? All right. Now, our goal is to solve for p, so in order to do that, we have to raise both sides to the e power. I don't know what the right way to say that is. We take e to the power of each side, because if we do that, that'll eliminate the logarithm, and you'll get p over p naught on the left-hand side. And on the right-hand side, you'll just have e to the all this junk. Right? And then I can multiply p naught to the right-hand side. So we get p naught multiplied by the exponential of negative mgy over rt. And that's the answer. This is the pressure as a function of y. And what it says is that if I were to plot pressure here and y here, okay, because y is like the dependent variable or the independent variable, then it's going to be a negative exponential with a value here that's equal to p naught. When y is equal to 0, you get p naught, and it's going to look something like this, asymptotically approaching the axis. This tells us that as elevation increases, pressure drops. That should make some kind of sense, right? Because as you go farther and farther up in the air, there's less air above you. And after all, the thing that actually creates air pressure is the weight of the air above you. That's where air pressure comes from. It comes from the weight of the air above you. So as you go farther and farther and farther up in the atmosphere, there's less air above you. So the pressure drops. And it drops exponentially, according to this equation. So like I said, less of a problem, more of a derivation. Does anyone have any questions? Ask a question then. Go ahead. We got time. We're just doing this and then one more thing and then we're done. The one more thing is going to take a while, but... Alrighty. So, oh, you mean it's a lot to take in, but it's pretty good. Okay, yeah, so something to keep in mind here, by the way. This whole thing that I did here by solving this differential equation, I suspect a lot of you have seen this before. Maybe some of you have, maybe some of you haven't. You're going to see this show up a lot in physics. And you might even see your professors throw questions on exams where they expect that you can do this. Okay? I've done it in the past. Doesn't mean I'm going to do it again, but I've done it before. And it's just something to keep in mind that you need to understand how to do this. Okay? It's the simplest type of differential equation that there is. And as you go farther along in your education, you're going to get professors that are going to kind of assume that you can do something like this. So, you know, kind of like look at the steps, make sure they make sense. You're going to see it happen a lot. You know, after you take differential equations, this is going to look trivial to you. Right now, it probably looks pretty complicated. After a semester of differential equations, this is going to be like child's play to you. You know what I'm saying? Because you're going to learn that there are way more challenging differential equations. There are differential equations that have no solution except to use a computer and just numerically model what the solution is. You know what I'm saying? So it's awfully nice when you have one that you can solve that, you know, the way I solved it, I didn't use any calculus you didn't know already, right? I mean, you all know how to take an integral, so... Anyway, just something that's good to know. I know in my 1C class on Monday, we're going to be doing this derivation. It's going to be the exact same derivation, except it's going to involve a circuit that has a resistor and a capacitor in it. And the answer that we get is going to look just like this, except that up here, it's going to have T over RC, which is just like a slightly different version of the same equation. You know what I mean? And then in a couple weeks, we're going to look at a circuit that has an inductor and a resistor, and we'll do the exact same derivation again. So as I'm saying, like, you're going to see this derivation a lot. You might as well try to understand what's going on, because you're going to have to do it at some point, probably. Alrighty. Yeah, I know for a fact that on one of my 1C exams, I gave them a problem. It wasn't something that they had specifically seen before, but they knew all the parts of it, and they had to be able to do this all the way down to this line to fully solve the problem. I think it was for extra credit, though, so don't get too scared. Alrighty, so let's do the kinetic molecular model of an ideal gas. This is really cool, I think, what we're about to do. Okay. I want to distinguish between macroscopic and microscopic real quick, okay? Don't worry about these things that are on the board here for now, okay? When we talk about a gas, there are what are called macroscopic properties. These are things that we can tell about the gas that apply to the entirety of the gas, okay? Examples of the macroscopic properties of a gas are things like temperature, volume, right? The volume applies to the whole gas. Number of moles, pressure, all the things that show up in the ideal gas law equation. Density. These are all what we call macroscopic properties because they describe the gas as a whole. If I tell you the temperature of a gas is 70 degrees Celsius, you know that that means that on average the temperature of the gas is 70 degrees Celsius everywhere. If I tell you that I have 2 liters of the volume of a gas, you know that that's the whole gas. It's not half the gas, it's the whole gas. It's not the volume of a molecule, it's the volume of the whole gas, right? Number of moles, same thing, it's for the whole gas. Pressures for the whole gas, density, etc. We call these macroscopic properties, and there may be more. We're going to learn later on about quantities called like entropy, for example. And I don't know, some other things too. Specific heat, I guess, is an example. Specific heat is an example of a macroscopic property too. Now that I think about it, but it doesn't change, so it's kind of different. Anyway, those are what we call macroscopic properties. We want to compare this to the microscopic properties. The microscopic properties are going to be the properties of individual molecules of the gas, okay? These are going to be things like velocity, the velocity of a molecule. When I think of an entire gas of molecules, what we're going to learn in this class is that the velocities of the molecules in a gas are random. Some of them are really fast, some of them are really slow, and we can talk about things like the average velocity or what's called the RMS velocity. We'll learn about that stuff later. But the velocity of a single molecule is a microscopic property that is going to be different for every molecule, okay? I'll just put over here. Okay, the velocity of an individual molecule. We could also talk about the mass of a molecule. We could talk about, this is all going to be of the molecules. So I'll just put that over here. So the velocity of a molecule, the mass of a molecule. We could talk about the volume of a molecule too, right? Not the volume of the whole gas, but the volume of a molecule. I hate writing this every time, but I mean, whatever. What other, you tell me, what are some other properties that you can imagine of individual little gas molecules? What other properties would there be? Spin, that could be what it is. How fast they're rotating. Okay. Density would be mass over volume, but sure. Maybe charge. Okay. Molecules have no charge though, so. Size would be volume. Size would be the same as volume. But spin's a good one. Spin or rotation rate. I want to be very clear here that I'm not talking about atomic spin. Right, I'm talking about not intrinsic spin, they call it sometimes. Just imagine a molecule that's wobbling around in space, right? Or rotating through space. That's definitely going to be something that's going to be important. What about location? The location of an individual gas molecule? That would be a microscopic property. Right? This is the location of a molecule is going to be something that's going to be relevant later on when we talk about entropy, actually. Okay. So, time, yeah. So I guess if you knew velocity and you know location, you can also describe how does the velocity change with time, how does the location change with time. So I think we could throw time in here too. I think that's relevant as well. When is it at that location, right? When is it at another location? When is it in the corner? We imagine one gas molecule and it's zipping all over the place, right? We freeze time and we say, I know where it is now. Can you tell me where it's going to be 10 minutes from now? That's a hard problem, right? If I tell you there's a gas molecule right here in the room, and even if I told you its velocity, it would be really hard to figure out where it's going to be 10 minutes from now. Would you all agree? Compare that to something that we understand really well, like the solar system. And if I tell you where Venus is right now relative to the Earth and the Sun, and you want to figure out where it's going to be, let's say 2 years from now, that's actually pretty easy to do. Because you can go look up the orbital period of Venus, right? You can go look up, that's all you really need, actually. If you know where it is now, and you know what its orbit looks like, and you know how long it takes to go around in an orbit, and I tell you, look in 2 years, tell me where it's going to be. Well, if the orbit has a period of 3 years, let's say, then you just need to look for it's going to have moved about 66% of the way around, right? That's easy. It's super easy. We know exactly where all of the planets in our solar system are going to be from here until the end of time, and we know where they have been for the last, I don't know what the right number is, at least for the last few million years, at least as long as the solar system has been formed in its current state. We know exactly where the moon's going to be. We know exactly where neighboring galaxies are going to be. You know what I mean? We know the physical location of so many different stars and galaxies that it just blows my mind, right? But when it comes to talking about the properties of an individual gas molecule right here on our planet, we know basically nothing about it. You know what I mean? We know nothing about it. All we know is that a gas is composed of tons of tiny little particles. These particles jiggle around a lot. Sometimes they rotate, but they move very quickly, okay? They move on the order of, if it's hydrogen gas, it might be 5,000 meters per second, which is about 10,000 miles an hour, right? So you imagine there's a little particle in this room, and it's zipping around at 10,000 miles per hour, right? That is so incredibly fast that it's going to be very difficult to predict what's going to happen in the future, because that molecule is going to bounce off all the walls probably hundreds of times within a few minutes, right? I mean, just imagine you're moving through this room at 10,000 miles an hour. It's not a very big room. So you're going to hit that wall, and then you're going to bounce off it at the ceiling, then you're going to bounce off at that wall. That's what I'm saying. You're going to have hundreds of collisions of a single molecule as it moves around a room. So as a result, it's going to be very difficult to predict where it's going to be. That being said, what we can do, and this is what we're going to do now, is we can actually make a connection from the microscopic properties back to the macroscopic properties, and then we can say, suppose that I know the temperature of the gas, can you tell me what the average velocity of the particles are? And the answer is yes, you can. And it's quite easy to do. So the goal here is, given some macroscopic properties, we'd like to be able to discover some of the microscopic properties, okay? Such as the mass of a single molecule, such as the velocity of a single molecule, and possibly what rate it's spinning at. Now, for the other two, location and time, we're actually not going to be able to get an answer to that. But like I said, later on, when we're discussing entropy, we're going to learn that we need to talk about the location and the possible locations that molecules can have in order to figure out entropy. So that's going to be one of the other things where we go from this thing and we create a macroscopic property that we call entropy. And what we're going to be doing right now is we're going to be basically going from velocity to temperature and pressure. The velocity of the molecules in the room are actually directly related to pressure and to temperature. And so that's our goal, is if I know the temperature, does that tell me something about the velocity of the molecules? And if I know the pressure, does that tell me something about the velocity of the molecules? Now, it's not going to tell me the individual velocity of every single molecule in the room because they're random. Just like rolling a dice is random, the molecules have random velocities, totally, purely random, actual random, real random, not like random in a video game where it's generated by a computer. I mean legitimately true randomness. And yeah, we can connect pressure back to velocity, temperature back to velocity, and we can get an understanding of where these things come from, basically. And that's what we're going to do right now. I think this is really interesting. I'm sure a lot of you probably will just be bored to death by what we're about to do, but I'm not. I find it super interesting. So, does what we want to do make sense? We want to connect the velocity of individual molecules to the pressure they exert on the walls of their surroundings, and to the temperature that thereby they create, okay? And I'm just going to tell you right now, fast-moving molecules are really hot. Probably not that surprising. Probably not that surprising that fast-moving molecules are really hot. Not too surprising. Anyone surprised by that? I'm not surprised by that. Fast-moving molecules will also exert a lot of pressure. That's not too surprising either, probably, right? Because if I have a molecule and it moves really slowly and bounces off of a wall, it's not going to exert much pressure. But if I have a molecule that goes really fast and then bounces off the wall, it's going to exert a lot of pressure. Okay, so in order to do this, we're going to make some assumptions. These are our assumptions right here. Let's go through what they say. All right, these are the assumptions. We're going to assume we have a container with volume V that contains a large number N of identical molecules, each with mass M. That's a pretty good assumption. I think that's a pretty good assumption. I mean, the idea of what a molecule is, right, is it's the smallest part of a substance, right? So I have a vessel. It's got pure oxygen in there. All those molecules are exactly the same, okay? We're going to assume the molecules behave as point particles that are small compared to the size of the container and to... Oh boy, look out, Louis. Louis, someone just screamed into your mic and it broke my ears. Please mute your mic, Louis. Or leave, that's fine too. The molecules behave as point particles that are small compared to the size of the container and to the average distance between the molecules. So, point particles. The molecules are in constant motion, so they never stop, ever. Each molecule collides occasionally with the wall of the container, and these collisions are perfectly elastic, meaning no energy is lost during the collision. The container walls are rigid and infinitely massive and do not move. Okay, so the container walls basically, we don't have to worry about them moving or anything like that. All right. Now what we're going to do is we are going to look specifically at number 3. What happens when a molecule collides with the wall of the container? So we've got a wall, right? We've got a molecule. It's coming in like this, right? It bounces off the wall, bounces off like that, right? So it comes in with some initial velocity here. It leaves with some final velocity over here, right? And what we can do, and as has been done in this picture, we can take that incoming velocity and we can break it up into its components, okay? One component is going to be Vx, which points toward the wall. And when it bounces off the wall, that Vx is going to go from negative Vx to positive Vx, basically, as the object bounces off of this wall. Now, when that occurs, what we can say happens is that there is going to be a change in momentum. So how much does it change? The change in the momentum, I'm going to use this p with a lowercase p basically to be momentum, should be equal to the final momentum, which is going to be the mass of the molecule times Vx, minus the initial momentum, which is m times negative Vx. So this, the change in momentum, is equal to 2 times the mass times whatever its x velocity was. Does that make sense? Same velocity in as velocity out. This is because it's an elastic collision. And there we go. This is the net momentum change for our molecule, right? Okay. We're going to come back and use that here in a second. Next. I think this part is the hardest part to understand, so kind of try to pay attention. Okay, let's read what this says here. So what we have here is, here's our wall, right? And you can see that there's a cylinder that's been drawn here. And so this is what this says right here. In order for a molecule to strike the wall in an area A, so you pick some arbitrary area that you call A, right? During a time interval that we call dt, So we pick an area and we pick a time interval, right? So we pick a little area, we draw it out there. We pick a time interval, okay? In order for the molecule to actually strike the wall, let's imagine the molecule started all the way over here at the edge of the cylinder. In order to get to the wall in the time dt, the maximum distance that it can be away from the wall is this quantity right here, Vx times dt. Because if it's farther away than that, it won't actually make it to the wall, right? Just to give you an example, suppose that the velocity x was 10 meters per second. Let's pick dt to be 1 second, right? What would the distance be here? If I tell you v is 10 meters per second and I tell you dt is 1 second, what would the total distance be? 10 meters, right? Okay, so any molecule that was 11 meters away, it wouldn't have enough time to hit the wall. Would you all agree? If it's 11 meters away, it's just not going to be able to cover that distance in that amount of time, right? So what this does is it allows us to create a volume within which we know that as long as the velocity of the molecules is this, they will hit the wall, okay? So let's put it all together, all right? So if I take this quantity, area times Vx times dt, okay? That gives me the volume. This is the volume of that, right? Now, if I multiply this by the number of particles in, so n is the total number of molecules that we have, divided by the volume of my container, the total volume of the container, this gives me the number of particles per unit volume, right? So if I take the number of particles per unit volume and I multiply by the volume, this gives me the number of particles within this cylinder that are actually going to hit the wall in that time. Does that make sense? So this quantity is the volume of the cylinder. Here, let me indicate. This is the volume of the cylinder. And if I know the total density in terms of numbers, the number density of molecules that I have, that's what this is. I'm not going to write that. I think it's going to be too confusing. If I take n over v and I multiply by the volume of the cylinder, I now have the number of atoms within this region that are actually going to hit the wall, right? So this would correspond to number of atoms or molecules now. I'm assuming all the molecules have the same x velocity. That's a big assumption that we are going to get rid of later, okay? For now, we're making this assumption. Assume that all the molecules in that volume have the same x velocity, okay? We know it's not true, but it's okay to start off with this assumption. We will be able to get rid of it later. Okay, so can you all see that if I do this, I get the number of atoms that it's actually going to hit the wall? Does that make sense? Okay. Now, the other thing we're going to have to do here, though, is we're going to have to say probably half of the atoms are moving left and half of the atoms are moving right. So really only 1/2 of these atoms are actually moving to the left, okay? And it's just their x component, really. So some of them are kind of going this way, and some of them are going this way, and their x velocities are all the same, but only half of them are left and half of them are right. So we need to multiply by half, okay? All right. Now, the next thing that we can do is we can say, if this is the number of atoms that will actually hit the wall, okay, then the total change in momentum, okay, the total change in momentum, I'm going to write it like this, dp, all right, should be equal to that quantity multiplied by this. Each molecule has a momentum change of 2 mvx, right? So if I have this many molecules, say it's 1,000,000 molecules, the total change in momentum is going to be equal to the number of molecules multiplied by the momentum change, right? That's going to give you the total momentum change. We can then divide the dt to the left-hand side. So we get, on the left-hand side, we get dp dt. On the right-hand side, the 2's cancel. And what I'm left with is n times the mass. This is the mass, by the way, of a single molecule. What's left? Nm area. Vx is now squared. And since it's squared, I'm going to drop these absolute value signs because as soon as you square it, it doesn't matter if you have an absolute value sign or not. And what's left? Volume? Just volume, right? Really, this is the change in x momentum. I should write it as px, like this. Okay. Now, here's the part where we see if anybody remembers this from Physics 1a. What do you get when you take the time derivative of momentum? What does that give you? Force. Yep. So this is force in the x direction, basically, right? Now what I'm going to do is I'm going to divide the area over here so that I have force over area is equal to nm Vx squared over the volume but what's force divided by area? Pressure. Yep. So there, we've kind of done it. We've now connected pressure, which is a macroscopic variable, to the individual velocities of molecules. And we also have to include their mass and the number of molecules per unit volume. This basically tells us that, you know, if we increase the volume, the pressure goes down. That's basically something we knew from before. Yeah. So anyway. And we can also turn this into another equation. We can write pressure times volume is equal to nm Vx squared, okay? Okay, so let's keep going because we want to get to temperature too. We got pressure, that's pretty good, but we want to get temperature as well. The next thing that we're going to say is that we're going to try to dispel what we said right here, okay? We assumed that all the molecules have the same Vx. It's probably not true. What we can say is that there's a relationship between the actual velocity of a molecule and its components, okay? In general, if I know that I have a vector, v, that's composed of a vx, a vy, and a vz, that if I want to find the size of the velocity, I can take the x component squared plus the y component squared plus the z component squared, and then I can square root all of that and I can get velocity. What we'd like to do, though, is we'd like to find the average value of these things. Let me see if I can write it in here. By averaging over every single molecule. Okay? This should still be true, this relationship, okay? And then what we're going to do is we're going to say, assume that Vx average, Vy average, and Vz average are all equal to each other. So that is to say that if I take all of the molecules and I measure every one of their x velocities and I take an average, and then I measure all of the y velocities of all the molecules, and then I take an average. We're squaring these things. Actually, if we just took Vx average, the answer would be 0. If we take V squared, though, it's not going to be 0. You know what I mean? Because if half the molecules are going left and half the molecules are going right, and I just take the average velocity, would you guys all agree that has to be 0? I've got some molecules going this way, some going that way. Okay, so if we take the square, though, it doesn't have to be 0, right? So the idea here would be then that there's really no reason to imagine that the average x velocity squared should be any different than the average y velocity squared should be any different than the average z velocity squared. After all, suppose that I pick a coordinate system and I say x is this way and I say y is this way and I say that z is in this way. And then you come along and you say, I want to take your coordinate system and I want to rotate it a little bit. Well, you should probably get the same value for the average velocities regardless of how you rotate your coordinate system, right? It shouldn't matter. So we can make this assumption that the average velocities are all the same. If we make that assumption, then this equation becomes the average velocity squared is going to be equal to 3 times the Vx average squared. The average x velocity squared times 3 should be equal to the average velocity squared, because if we make these all equal to each other from this equation, then you get this equation. That means that Vx average is equal to the average velocity squared divided by 3. And the other thing that we can say is, we made this assumption. I'm going to scroll back up just a little bit here. Why did I didn't mean to put that on there. That should be a squared. We made this assumption that all the molecules have the same Vx, and that was kind of a silly assumption. What we can do instead is say, instead of using Vx squared, if we replace this with the average velocity squared, okay, so if we take our equation right here, right, we take that equation right there, and we now replace this with the average x velocity, this becomes a lot more reasonable thing to say, that the pressure times the volume is equal to number of molecules times the mass. If we put average velocity in here, we no longer have to assume that all molecules have the same velocity, right? We can just say, well, some of them have a higher velocity than this, some of them have a lower velocity than this. On average, they have this velocity, and it's okay because we're talking about the average now, instead of talking about the actual velocities. The average is certainly a number that we can use to talk about, okay, if on average this is what their velocity is, I can figure out the number on average that will hit the wall, right? And then what we do is we make this replacement here. So this is equal to nm over 3 times the average squared now. So we drop the x thing, right? And then what we're going to do is we're going to put this in terms of something that we've seen before. You'll notice here that you have mass times average velocity squared, right? So the other way that we can write this is to say pressure times volume is going to be equal to 1/3 of n multiplied by, I'm going to write it like this, 2 over 3. So I'm going to multiply by 2 over 2. nm times 1/2 m, the average squared. Oh, I got too many n's now. My bad. There we go. Would you all agree that if you go from this line to this line, I haven't changed anything? All I did was multiply by 2 over 2. And now what we can do is we can say that this is the average kinetic energy, basically, right? Make sure that just make sure I'm saying it right. We're going to write this as 2/3 n times k trans. So what this is going to represent here, this is the average translational kinetic energy of a single atom. Okay, because it's the mass of a single atom, the velocity of the average velocity of a single atom, which means this is the average translational kinetic energy, and so we get that nice relationship right there. But the other thing that we can do is we can say, wait a minute, we know from before that PV is equal to little n times r times t, right? So what we can say is that the translational kinetic energy then, right? Hold on one second. I think I said something that's wrong. Okay, this is the way that your book writes it, actually. Sorry. Okay. Yeah. Notice what we've done here. This says n multiplied by this. This is the average translational kinetic energy of a single atom. If you multiply by n, what do you get? You get the total translational kinetic energy, right? The total translational kinetic energy of the whole gas. It's given by this expression. And then what we can do is we can say, compare this to this. So if I put in here 2 over 3 k trans, this is equal to nRT, which means I can find the translational kinetic energy for my gas also by doing 3 over 2 times nRT. So that's an equation you're going to need. Okay. And then the next thing that we can do is to take this equation here and say that translational kinetic energy is also equal to 1/2 mv average squared divided by capital N. That's also what translational kinetic energy is. And that this is equal to 3/2 nRT. Wait, how do I do this next part? Yeah, I'm doing it right. 3 nRT sorry. I'm confusing myself. Let's try this again. Okay. K trans is N times that. My bad. Yeah, that's right. Thank you, Jake. Okay. It's N times 1/2 little m v average squared. Okay, that's here. My bad. This is equal to 3/2 nRT. Okay. And now what we do is we divide the little n to this side, the big N to this side. So we now have 3 nRT divided by big N multiplied by 2, right? And now what we need to do is we need to say that little n divided by big N, what is that? Let's write over here. Let's come over here and write what that is. So little n divided by big N is like saying moles divided by atoms, right? Because big N is the number of atoms and little n is the number of moles. If I take moles per atoms, what's that equal to? What did we learn about at the beginning of class that's written in terms of moles per atom? Yeah, Avogadro's number. So this is 6.022 times 10 to the 23 atoms per mole. Well, like this, right? It's upside down, right? That means that this is equal to 1 divided by Avogadro's number, which I'm going to write like this. So Na is Avogadro number. That is to say it's this, right? So in our equation here, what that becomes is 1/2 mv average squared is equal to this over this, so you're going to get 3/2 r divided by Na t. And now we're going to get a new constant that you're going to see show up a lot in this class. So we're going to define Kb to be equal to r over Na. Okay, Kb is what's called Boltzmann constant, and it is equal to 1.381, or one, usually just I write it 1.38 usually. 1.381 times 10 to the negative 23 joules per mole Kelvin. So it has hold on, let me think about this for a second. Avogadro's number is atoms per mole. I think it should be joules per molecule, right? It's not mole. Yeah, that's what I thought. It's not mole. It's not mole. I didn't think that was what it was. Sorry. Oops. It's joules per molecule. Or joules per atom times Kelvin. Okay, so this molecule it's usually just written as 1.38 times 10 to the minus 23 joules per Kelvin, actually. You usually don't write the molecule part. Right? Yeah. Yeah. It's usually just written like this. Joules per Kelvin. It's a very straightforward number. It's a tiny number, right? But what it tells you is that for every 1.38 times 10 to the negative 23 joules you have, that corresponds to like 1 Kelvin, basically. Anyway, given this definition, we can take that equation, replace R over NA with KB, and we get our final relationship, which is that 1/2 m mass of a single atom times the average velocity squared is equal to 3/2 kT. This is the equation you're going to use a lot in this class. We'll use it a lot in derivations, and there's other versions of this as well, but this is the main one right here. It relates directly the average velocity of molecules to their temperature, and it tells us that if the temperature of a system increases, what happens to the average velocity? It goes up. Hot objects move fast. That's what that says. It says hot gases have molecules that are moving really fast. And it basically tells you, that equation tells you what temperature is, right? It tells you what temperature is at the microscopic scale. Temperature at the microscopic scale is kinetic energy, right? And temperature is a way to measure kinetic energy. Does that make sense? All right, so that's the end of tonight's lesson. We went over a little bit. That's okay. Hope you all enjoyed it. I'll stick around if there are other questions for a little bit.